For loops and while loops are incredibly important in programming. They're used all the time. So in this video we're going to do two extended examples, one with while loops and one with for loops. The first example is going to be that of the higher and lower game, which we saw in an earlier video. You will remember that in that game the computer chooses a number between 1 and 100 and we have to guess it. If our guess is wrong, the computer tells us whether it was too large or too small, and the game repeats until our guess is correct. In other words, it repeats while the guess is wrong. So a while loop is the perfect thing to solve this problem. Let's solve it in this code cell here. So in the first two lines there, we generate a random number between 1 and 100 and call it secret. You'll learn about the import statement and about random.randint later. For now, just take it for granted that what happens when we run those two lines is that secret is a random number between 1 and 100. So what we'd like to do is keep doing something while our guess is wrong. In other words, while whatever the guess is not equal to the secret. So we should begin with a while loop which checks whether guess is not equal to secret. Then we should get the next guess, and you'll remember that we can do that using the input command. If we give the input command a string as its input, then it will print out that string and then ask for an input. And you'll also remember that there is a problem with the input command for us in that the output of the input command is always a string, whereas we need a number so that we can compare it with the actual true secret. To convert the input into an integer, we can use the int function, as we saw before. Now that we've got the guess, we're ready to compare it with the true answer, the secret, with a conditional. So we should begin by checking if the guess was too big. If the guess was larger than the secret, then we should print out the message too big. And that's all. Now I need three different possibilities. Either the guess is too big or too small or just right. So to allow me to have three possibilities, I can use an else if, elif. If the guess is less than the secret, then again we will print out a message too small. Finally, if neither of those two conditions was true, then the guess must be correct. So we can add an else, and if we enter the else, then we know that the guess must be right. So we will simply print out the message you win. That's all we need inside our while loop. We're ready to go. Except there's a problem here. So what's going to happen the very first time Python enters the while loop? Pause the video and think about it. The very first time we enter that while loop, there will be an error. The problem is that when Python first gets to line 5 here, guess has not been defined. So when it tries to compare the guess to see if it is not equal to the secret, it'll throw an error because guess hasn't yet been defined. So I need to give guess a value just so that we don't suffer that problem when we first enter the loop. So what value should I give it? Well, if I give it a number between 1 and 100, then there's a small chance that it might actually be the correct answer, in which case we'd never get into the while loop. So I should give it a value which cannot possibly be correct, like -1 for example. Now we're ready to go, so let's run it. I enter my guess, which is 50. 50 was too small, so let's try 75. That was too small. Okay, let's try 87. That's also too small. So if we try 95, that's too small as well. 97, too big. So I think I know what the answer is. 96. I've won the game. Okay, so you can see that it seems to be working, and it has stopped when I got the guess correct, because when my guess was correct, when Python checked on line 5 where the guess was not equal to secret, it would get the answer false, and so it would continue with whatever came after the body of the while loop. But there's nothing after the body of the while loop, so it would just stop. Okay, our next example is about for loops. And we're going to investigate something called Euler's conjecture, which was that the sum of fewer than kth powers of positive integers can't equal another kth power so long as k is bigger than 2. And it so happens that Euler's conjecture is false. This was discovered by people called Lander and Parkin in 1966, and they published a paper about this because it was a big deal at the time. Nobody knew that Euler's conjecture was false until they found their counterexample. So here is the entirety of their paper. The title was Counterexample to Euler's Conjecture on the Sums of Like Powers, and the text of the paper was, a direct search on the CDC 6600 yielded something to the 5 plus something to the 5 plus 110 to the 5 plus 133 to the 5 is equal to 144 to the 5 as the smallest instance in which 4 fifth powers sum to a fifth power. This is a counterexample to a conjecture by Euler. As you can see, somebody has blacked out the first two numbers in their counterexample. What we're going to do is to look for how to look for those two blacked out numbers. By the way, a CDC 6600 was an early supercomputer. It was a mainframe computer made in 1964, so it was the absolute state of the art at the time that Lander and Parkin solved this problem. It was the fastest computer in the world in 1966. It had about 30,000 times less data, less memory than the phone in your pocket, about 60,000 times less storage than the phone in your pocket. It was the size of a small room, and it cost $8 million in 1966 money, which is about $60 million today. Here's a picture of the CDC 6600. Oops, there we go. As you can see, it really is the size of a small room and has its own built-in desk as the display unit. If you look carefully, just in the corner of the photo there, where my cursor is pointing, you'll see a little bit of copper piping. That's because the CDC 600 generated so much heat that it had to have its own built-in Freon refrigeration unit. Anyway, let's try finding those two missing numbers. So I'll scroll back up to remind you what we're looking for. We're looking for the two numbers whose fifth powers added to 110 to the power 5 and 133 to the power 5 equal 144 to the 5. So if we call those numbers A and B, then a simple way to find A and B would just be to try all the possibilities. You can see that these numbers must have at most 3 digits, just looking at the size of the blacked out part of the text. So if we try all the possibilities for A with 3 digits or fewer, and all the possibilities for B, then eventually we'll come up with the right answer. This technique of trying all the possibilities is called brute force search. And it's the stupidest possible solution to the problem, but it just might work, especially for small numbers like this. So that's what we'll try. We're going to use a for loop to generate all the numbers A between 1 and 1,000, and then for each of those numbers A, we'll try all the numbers B between 1 and 1,000. So to do that, we're going to need a for loop for A and a for loop for B inside the original for loop for A. So 2 nested for loops. So here's the code that we need. We'll start off with a for loop which is for the first variable A, and it is for A in range 1,000, which you'll remember runs over all the values of A between 0 and 999, so all the values with at most 3 digits. Then inside that, for each value of A, we're going to try each value of B between 0 and 999. So we need a for loop inside a for loop, and this means for A equals 0, we'll check all the possible values of B. Then for A equals 1, we'll check all the values of B. Then for all the value A equals 2, we'll check all the values of B, and so on. And between them, we'll check all the possible pairs of A and B between 0 and 1,000, and thereby find somewhere the counterexample from the paper. So line 1, we have the for loop for A, and then line 2, we have the for loop for B. That means on the next line, we have to have 2 layers of indent because we want to have a code which is inside both for loops. On line 3, we've got the conditional that checks whether A to the power 5 plus B to the power 5 plus those other fifth powers is equal to 144 to the power 5. If that's true, we found our counterexamples. So on line 4, we print them out. We have a print statement which just prints the values of A and B. And you can see that this now has 3 layers of indent because it's inside a conditional, inside a for loop, inside a for loop. And that's really all we need to check to find what the values of A and B are. So let's run it and see what happens. So it runs very quickly indeed because it's only checking a million different arithmetic operations. So there's a million different equalities. So there's not a lot of work for Python to do there. It can do something like that very quickly. My laptop is not super powerful at all. It's 5 years old. So you can see it spits out both 2 answers here. And of course, we should expect 2 answers because if AB is a solution, then BA will be a solution as well. So we found the 2 answers, 27 and 84.